Hey guys, this is Shi from the Texas Tech University. Today I'm recording this video to give a demo for the xBGAS toolchains. Through watching this video, you're probably going to learn how to play with the xBGAS toolchain based on the, or let's say the xBGAS extension based on the standard RISC-V ISA. So if you take a look at the repo of the xBGAS toolchain, you'll find a folder called xBGAS assembly test. In this folder, so basically it contains all this assembly code, basically all the extended instructions from the RISC-V in the xBGAS. So the purpose of this assembly test is not to to give you to write a benchmark to help you build your own application. It is not. The purpose of this is to verify the encodings. So let me show you how it works. So first, if you run the make, what it actually does is it will basically compiling and assembling all the files, and then it will disassemble the file and compare the assembly code if they're the same or not. If the two files are matched, which means the encodings are correct. Otherwise, we have a conflict in the encodings. So if we dive a little bit deeper, we can see, what is that? Let's change the directory to the test, to the C file. You'll see all of those just different kind of benchmarks. For instance, if you open the raw loader store .c file, you will see this is very simple. Let's say the C file. As you can see here, they have some initialize the data, and then you can take a look at the raw load and stores. As we can see here, this is just basically testing all the extended instructions, the extended raw load and store instructions, including the address management of the xBGAS. However, if you directly run the test, you're probably going to find something like, let's say you npm run and two threads and spike -x, let's say pk raw exe. You'll find something like this. It's a segmentation fault. The reason of this is because the address, because as we can see here, all of this kind of registers are actually uninitialized. So which could happen is if you forced it to load from the address stored in the A6, the E10, you're probably going to see that the address are uninitialized and the segmentation fault occurs. So again, as what I just said, the purpose of this assembly test is just to verify the encodings. So we can also see the diff file, the diff. This is basically used to compare with the assembly, let's say the code that has been disassembled from the binary, to compare to see if the encodings are the same or not. If it's same, then it'll be okay. But otherwise, you probably need to make a double check on the encodings. So this is basically pretty much the assembly test. And so remember, there will be one of the tests are actually could be executed. Let me see. It should be vi raw v2.c. So this file, as we can see here, after the normal initialization, we actually force each assembly instruction and pass it with an argument to make sure that all the addresses are valid and all these load and store instructions will not cause any segmentation fault. So in this manner, if we run the same, let's say, use the same way to execute the program, but this time we use the version 2, yeah, you'll see it executed successfully, and there will be no warnings or errors. So this is pretty much the xBGAS assembly test. And then let's take a look at the runtime libraries of the xBGAS. So this is basically providing all the users an API on how to use the xBGAS extensions. As we know that it will be a little bit painful to directly write assembly code in your, like say, on your own benchmark or applications. So we provide this, that's a C language-based interface for the xBGAS, let's say, the extensions. So basically, what you need to do is just utilize the function calls we provide, and you can write your own applications. So let's first take a look at the test file. Let's say we have three different folders. The first one's Alex, the second one's init, and last one is the transfer. So it represents the first one, the first category of the test, for instance, allocate. It contains all this tests on the data allocations. For instance, let's say, let's take a look at the alloc test 1.c file. You find out what it actually does is, first, it will do the xbr time init. So basically just do the initialization. Every time you run xBGAS, you need this. And then you run the xbr time malloc. So basically it will tell the runtime that, okay, now you would like to have that much large memory shared by each PE, we call it processing element, or let's say the thread. And then just directly free it. So this is the purpose of this. Just basically keep running keep allocating the data to see if the problems occurs or not. Just a basic functionality test. And a second folder, init. So basically doing the different kind of initializations. If you take a look at the init test 1.c, you'll see what it does is just run xbr time init and then xbr time close. So this is a function call you need every time. These two function call you need every time you like to use the xBGAS to write the application. At the beginning and the end, you need to do this. And we'll take a look at some other files, same init folder. This one doing something similar, but more than that, it's testing some more features. The first one is xbr time my PE, basically my processing element, my thread ID. It will return the thread ID of this the current processing element that is calling this function call. The second one is xbr time number of PEs, basically telling you how many threads are running simultaneously right now. And then besides that, all the rest is the same. Init first, then the xbr time close at the end. If we want to run the test, we can just change directory to test bin, and we have all those kind of tests. So every time we run a test, we use the npm run, the -n specified number of threads you like to have, and then run a spike. Remember to enable the xBGAS, use the -x, give it a just whatever you would like to pass, like the memory size. So currently, at the time I'm recording this video, we don't really use these digits, no matter it's 1 or 512. It doesn't really matter because we make everything shared. But at the beginning, when the first time we designed this something like the portal, we would like to provide the users the choice that how large the memory they would like to be shared. But the things we also have the malloc inside, xbr time malloc inside of the xbr runtime as a function call that the user can directly manage it inside of their program. So we kind of like drop this functionality, but we still leave this portal here just in case in the future we would like to switch back to this choice or whatever. So after you enable the xBGAS, you run proxy kernel, and let's say if you run the init test 4, you will see something like this. Basically, to print out after initialize the xBGAS runtime, it would do the the p equal to 0 of 2 total p. So basically, the current p, the thread ID is 0, and totally we have 2 threads, and then xBGAS is closed. So quite simple and clear. Besides that, we can take a look at something more complicated. It's basically doing the data transfer. So first, let's take a look at the transfer get test1.c. So at the beginning, as we can see here, they have the xBGAS alloc size. So basically, we define the size of the shared data. So basically, also the variable is used here, and then we have the xbr time init xBGAS, then allocates the shared data. The size will be 8 bytes. And then after all the data has been initialized, before you do any data transactions, remember to run the barrier first. It'll be a little bit different from the normal, let's say, API or runtimes like the MPI or the OpenP. You have to run this before you would like to perform the data transfer, because the currently the xBGAS toolchain are based on the RISC-V toolchains, or let's say the Spike simulator. So what Spike does is every time when you boot a Spike, it automatically or by default allocate 2 gigabytes memory for you. So you don't really need to manage the data allocations and address mapping stuff. However, if you don't have this xbr time barrier, what's going to happen is it could happen that one of the thread finishes all of those and directly jump to this, let's say the data transactions. However, some of the data may not be ready. Some of the thread may not be ready. In this case, it could cause a segmentation fault or the let's say the mismatch of the barrier or locks. So this is something we like to avoid. So always keep it in mind. Use XBR time barrier before you would like to perform the data transactions, and also after you finish all the transactions, before you would like to exit the program, run XBR time barrier again to make sure everything works all right. And then within this two barrier region is actually the, let's say, the data transaction part as the remote memory accesses. So as we can see here, this function calls XBR time unsigned long get. So basically, you're transferring the unsigned 64-byte integers. And the variables represent the destination, the source, and the number of elements, the stride, and the target. So now the XBR time might be equal to 0, which means if the thread ID is equal to 0, it will transfer the data to the thread number 1. And then the size of the data, the element, the number of the elements that they would like to transfer is only 1, because the data allocated here is only 8 bytes. So basically just one 64-byte unsigned integer. And a stride is basically used for loop unrolling. We're gonna introduce that a little later. Because now we don't have one element to transfer, so the stride will also be set to 1. So what it actually does is just to transfer the 8 bytes data from the thread 1 to thread 0 through the XBR time get functions. And now let's take a look at something a little bit more complicated. Let's say now the same data size, same data type, but we have more elements. Now we have 1K the elements that we would like to transfer. So same thing again, after init and the malloc and the barrier, we have to do the data transactions. But this time, after destination and the source, we see the NE, which is the number of elements defined over here. It equals to 1K. So what's going to happen is this function call will transfer the 1K unsigned 64-bit, 8 bytes integers. In this manner, totally we're going to transfer something like 8K, 8 kilobytes data from the thread 1 to thread 0. So this the NE inside of the runtime implementation, we actually perform the loop unrolling. It's just like a technique we do to optimize the executions, to avoid the branches, and also to maximize the parallelization in the code execution. And that is basically the only difference between the, let's say, the first example we showed is only 1 here, and now we have the NE here. So basically we provide the flexibility, just like the MPI calls or OpenSHMEM calls, that we can specify the length of the data that we would like to transfer. And I'll show you at the end of the test that what is the performance difference between these two. So if we switch to test Bing, now we can just feel free to execute all those kind of instructions. So if we do, for instance, if we would like to run first, let's just get 1 8-byte data, basically the transfer get test 1 we showed at the beginning. You will see this. And this initializing the xBGAS runtime, and after initialized, allocating the data, the shared data, and then it pointed out the address because of the spike simulation. Let's say the spike simulator, they provide the same address mapping all the time if the data size is the same. So basically, you will have the same virtual address or physical address, but it's on a different node. And then executing the barrier. The thread 1 we're doing nothing because it's just waiting the thread 0 to complete the operation, basically load the data from the P1 to P0. And after everything finished, the xBGAS is closed. And also let's take a look at the unrolled version that we basically transfer 1K 8 bytes unsigned integers. You'll see something like this. The allocated size becomes different, and they go through the same procedures, but just transfer more data. And then probably one more thing I need to mention here is, one more thing I probably need to mention here is, at the end of the program, remember to free the pointer you just allocated at the beginning. So basically the shared memory over here that I allocated over here should be freed. That's another thing, if you write the program, you should pay attention to. This is pretty much the xBGAS runtime test. So I just showed how the program is organized, and when you write a program, what kind of points you need to pay attention to. And if you want to test all the tests, basically all the runtime tests, what you can do is just make first run make, and then into the build directories, make clean and run make. This is basically how you build the two chains, and the next thing you would like to do is just simply run the make test. And what is going to happen is it will just automatically use a C test to run all the tests to see if the test passed or fails. So by default, all the tests should work all right, and we have tested the multiple times, so it should work perfectly. And besides this, we also have some extended tests. Besides the let's say the xBGAS runtime and also the xBGAS assembly test. It's called extended xBGAS test. We're probably going to push it into the official folder, or probably a part of the xBGAS runtime repo, but it's going to be something after the supercomputing 18. And we're probably going to, in the meeting, we discuss the details, and then just push forward to just get out more benchmarking stuff to show the capability of the xBGAS. So right now, what I can show you guys is the xBGAS test. So when you try to compile the xBGAS program, now we have, let's say, something like 9 different kind of benchmarks. Some of them ported from the OpenSHMAM, the official test is used. Some of them are from all different kind of the data-intensive applications benchmark. So let's first take a look at the makefile. So in this makefile, all what you need to do is the first thing is just try to specify. The compiler of the xBGAS, basically the RISC-V compiler, unknown ELF GACC, and also remember to specify the path of the RISC-V. This is another very important environment variable that is also widely used in the standard RISC-V toolchains. And besides that, something else we need to pay attention to is the C flags. Just make sure that you have the XBR time, where you actually install all this kind of header files and the lib file. So basically the XBR time library. So when you run the test, just make sure that you link the statistical library perfectly, and the program should compile fine. So if we run make, everything compiled perfectly, no problem occurs. So now we have all the benchmarks compiled. And first, let's take a look at, let's go through the benchmark one by one. The first one I want to show is the scatter and gather. Scatter, the C file. For the scatter and gather benchmark, what it actually does is pretty simple. So for the scatter gather, the only different from the normal data transaction is the random memory accesses. So first we have the shared data and the private data. The shared data is actually allocated through the XBR time. So basically, if you want some data to be shared with all the other kind of different processing element, you need to use XBR time malloc. And if you want to have the local data, private data, then just use a normal malloc. It will be okay. And we use XBR time init for sure, and then use the random data to generate the index. And the shared data will be set to the corresponding PE, the respective processing element ID. So if you take a look at the index, so the index value could be larger than the size of the array, let's say that no matter private or shared. This is because we kind of like in the PGAS applications, we distributed the array evenly into all the threads. So suppose now in this array we have 1K different kind of the size of the array, shared array is 1K. Then in this manner, totally we will have 1K times PE. This is how large the entire array of this application. And then inside of the scattering procedures, what actually does is first get the target, so which thread you would like to access. So what actually does is use the index and then divided by NE number of elements. So suppose the total size will be 5K and the number of elements is 1K. So basically if you use a 5K divided by 1K, you got 5. Then targeted thread address will be 5. Similarly, the index will be obtained from the index index I minus the target times the number of elements. Basically gets the local ID of the place that where the data is allocated. So after you get the index, we have two different kind of choices. The first one is the index is actually or let's say the target is actually equal to the current PE, which means the data is stored in the current processing element. In this manner, we just do a local accesses. Otherwise, we have to do the remote put, basically put the data to the remote node. And same thing, the first argument is destination, basically the shared index. Index is obtained right over here. And then the next one is the source. Basically, the address of where the data is located is a local private array. And then number of elements will be 1, and the stride will be 1 because there's no loop unrolling here over here. And the PE is just the target of the thread that you would like to get or put data there. And then this is going to be the remote memory accesses. And after the transactions, we have the barrier, and just all the rest just calculating the time and print out the informations. And again, remember to free your data at the end of the program. So if we run the application, regarding this, I wrote a small script over here to simplify the procedure. Just basically, again, just MPI run and a spike, and just in case your program has some other arguments, just put it over here. Just to make it a little bit easier for the demo. So xBGAS, let's say first, let's use the 2 threads and run the scatter benchmark. Scatter, and what's going to happen is it'll have something like this. xBGAS running the scatter with 2 threads, and this is the total data size, the element number, and number of the processing elements, and the basic number of threads, and the time of the data initialization, the time of data transfer, and then also record the percentage or let's say the requested distributions. The red representing the remote accesses, and the green one represents the local accesses. So this is pretty much the percentage of the the requested distributions. And if we change the thread number a little bit, let's say now we want 4 threads running simultaneously, what's going to happen is the same data size per thread per processing element, but the different thing we can see here is the more time for the data transfer and the initialization, and also the remote accesses. The percentage of remote accesses increased a lot. So basically 25%, I'll say a quarter of the data at local and all the rest are remote. This is because now we have 4 threads, and the shared data are evenly distributed to all the processing elements. In this case, we see something like this. And similarly, if we have more threads, we will see something similar. Let's say 8 threads, then we have more remote accesses. And oppositely, if we run the gather benchmark, it basically does exactly the same thing as the scatter, but the opposite way. So the scatter is basically scattering data to all different kind of PEs, but the gathering is gathering the data from all different kind of PEs. So if we run the data, you will see the similar results because all the index are randomly generated with different seeds. So you will see the percentage will be quite similar, but the timing are actually different. And besides that, if we take a look at the source code of the gather, you will see the big difference is just the use unsigned long get. Rather than put data in the scatter, we get over here. That's the only difference. And all the rest of this benchmark will be the same. And besides that, let's take a look at another benchmark we wrote is the matrix multiplication. Oops. So for this benchmark, so what it actually does is we assume that we have 2 threads, we have 2 processing elements, and what it actually does is first the processing element 0 will first get the data from the processing element 1, basically transfer the array from the remote to local, then do the matrix multiplication. but we have two different ways to do it. The first one is inside of the the first one is actually just use the NE. We transfer the entire array just within one function call in the xBGAS runtime. So basically, the NE here equals to the size of basically the xBGAS number of elements times 8. So basically, probably going to be 8K. And then the second one is inside of a for loop to perform the data transactions. And then we compare it's over here. The fetch via the loop. So basically, inside of the for loop, and every time we only fetch one element at a time. But in the for loop, we just repetitively fetching the data from the remote processing element. And if we run the, say, matrix multiplication, we'll see something like this. So number of elements is 8K, and data type is unsigned integer 64-bit. So totally going to have the 64 kilobytes data, and the P number equals to 8. So we have 8 threads running simultaneously. But as we can see here, the point we would like to show is raw transactions and coalesced transactions. The raw transaction representing we don't really combine the data, so we fetch one element at a time. So as we can see here, the time difference is actually pretty large between the raw transactions and combined, or let's say aggregated transactions. That it's just basically in one function call, we basically transmit all the data. And inside of the runtime library, the loop unrolling is basically the current optimization that caused this performance difference. And then probably in the future, we're gonna really do the memory coalescing, or let's say the data aggregations. That in the Spike simulator in the ISA level, we try to have this support to further reduce the logs of the message queue, so that the overall performance can be further enhanced. That's basically the matrix multiplication benchmark. And then let's take a look at the k-means. This is the application ported from the standard MPI version. And as we can see here, if we run the k-means and give it an argument, the argument here I specified here is just the number of clusters you would like to have. So suppose we would like 8 clusters and 2 threads. What's going to happen is it'll just keep running. For now, the size of the data, basically 4 kilobytes, and the dimensions of the data, the number of the element, and the cluster number, the number of the processing element, and the overall time cost. And eventually print out the cluster and the cluster size besides the cluster center. That's basically how the benchmark works. If we take a look at the source code, there's not something that special. The only thing we have is just try to port the MPI reduce calls and all the other kind of MPI function calls, broadcasting, the reduce, to the xBGAS runtime version. And then it's very likely that we will have a dedicated function call that serves this feature. But right now we just use the normal load and store to let's say to simulate this behavior. So after data initialization, just run the k-means, and just and after that, just point out the respective cluster center and the cluster size. So if I take a look here, here is actually the function call of the xBGAS, MPI broadcasting. Two different, let's say the MPI bcast call. And what we have to do here is we have to manually transfer the data, because now we basically the code here is hard coded. So we only work for the 2 threads version. That's the thread 0 basically get data from the thread 1, and then we basically do the broadcasting or reduce. But yeah, again, in the future we're going to change it with a unified function call, and then after that we will convert this benchmark to the also release limitation to the 2 threads. We can make it 8 threads, 16, and whatever. And then theoretically, the our xBGAS runtime support up to 1024 number of processing element running simultaneously. And so by default, we should support up to all this kind of threads running to support, basically using the MPI to do this. And besides this, the rest of the function calls are just the benchmark ported from the OpenSHMEM test suits. And I think one of my colleague, Brody Williams, he's gonna give a small demo as well, telling you how to run that kind of benchmarks. So I won't spend that much time to repeat the same thing. So I'm just gonna give a very brief introductions. For instance, if we want to take a look at the shmem all, basically it's doing the MPI all function calls. Take a look at the code first. So what it actually does is quite simple. First, after all the data initializations, it basically have two shared data. The first one is the sending counts and the receiving counts. And it's seed random with the my ID, or say the my PE, and the core part is broadcasting the data or sending data like all version. So we will have the for loop over here, and every time in the loop, the ID or the address, the local address of the R counts will be the same because ID is the same per P. Inside of the same P, it will be the same. And the sending count, this is basically the source, this is the destination, and this is the number of elements, the stride, and the node ID. So for the node over here, node ID is actually incremented from 0 to the largest processing element ID. In this manner, it ensures each thread sends the data to all the rest of the threads. So that the MPI all function calls are actually realized. So if we run this benchmark a little bit, and we will see, suppose I just say let's say now first we use the two threads to run the benchmark, and we will see something like this. So data size, element size, two processing element. The first my ID equal to 0, the sending count is 0, 0. My ID equal to 1, the sending count is 1, 1. So the data in the sending count is equal to the value of the my ID. And after the data transactions are completed, we will see the receiving count will be 0, 1 and 0, 1 because we do the broadcasting. So the thread 1 will send the value of its own my ID to the respective index in the receiving count. So the second element will be replaced by 1 in the thread in the P0, and similarly the first element in the P1 is reset to 0. It just doing all function calls, and if you have more threads, we probably have a more let's say a better view of how everything works. So again, the sending count will be the equal to the value in the S counts were equal to the corresponding my ID. It basically incremented from 0 to 7. And then in the receiving count, after broadcasting, it should just incrementing from 0 to 7 because it's just what the broadcasting works. And then it pronounced the corresponding time cost. So this is pretty much how to, let's say, run your xBGAS toolchains, how to write your xBGAS benchmark, and how to compile it. If you have any other questions or problems with executing or running the xBGAS benchmark, let us know. And all the repos are in the public release. Feel free to submit the issues or send us email if you have any other questions. Thank you for watching this video.